Hello everyone, welcome to my virtual presentation. My name is Daniel Aguilar Marciac. I'm a PhD student at the University of Colorado Boulder in the Department of Aerospace Engineering Sciences. Today I'll be talking about the work that I did as a summer intern at Mitsubishi Electric Research Laboratories with Stefano Di Cairano and Avishai Weiss. This work is related to spacecraft Rendezvous, and in particular I'll be talking about fail-safe rendezvous control on elliptic orbits using reachable sets today. I just want to give a brief introduction of the rendezvous problem for spacecraft missions. We can see an illustration of that here on the top right, where we have like the Dragon capsule by SpaceX going to dock with the International Space Station. So typically we have a control chaser, which would be the Dragon capsule here, which aims to move towards and remain near target body. That could be the International Space Station, a different satellite, or even an asteroid like Bennu. And indeed, rendezvous is important for several reasons, to further human exploration, for spacecraft servicing and maintenance, since we know there's going to be numerous satellite launches in the coming years. We're going to have record-breaking constellation sizes, and potentially some of these are going to require servicing and maintenance, which will inevitably require rendezvous and docking procedures being done. It's also obviously important for the acquisition of scientific data to understand our solar system. But the challenge really lies in automating this process, and especially when you're trying to do this in an inherently safe approach. And that's the topic of discussion in this talk. So here we have the rendezvous description. Geometrically speaking, we have the inertial frame that's centered at the center of mass of a central body. This could be the Earth. We have the chaser spacecraft and we have the target. These are their inertial position vectors. They are both orbiting the central body, and what is of fundamental importance really is the relative position vector of the chaser with respect to this target, since we will be using this throughout the safety analysis and ensuring that our safety is not compromised. We also have a notion of a hill frame, which is a special kind of coordinate frame that's attached to the target right here. It moves with the target along its orbit, so it's a co-moving frame. It's just useful to map relative positions and velocities into this frame because of visualization purposes, but also because we can see what the states of the chaser would look like as seen by the target. So we'll be using this throughout our implementation here and in the figures I'll show you later. So the goal of safe spacecraft rendezvous is really to minimize some kind of performance metric while satisfying your safety constraints. This performance metric could be fuel consumption, control usage, or something similar. The particular kind of safety we're interested in here is that known as passive safety. So this would be the case where, despite a total loss of control, your chaser would be on a free drift trajectory that avoids entering some sets. Those sets are going to be defined now as the approach ellipsoid or the keypad sphere. They're both centered at the target, so in the hill frame they're centered at the origin. The keypad sphere is contained inside the approach ellipsoid, and we use these two sets to basically quantify and in some sense qualify safety. It's a strict requirement for many missions that we have to be able to guarantee passive safety of our trajectories or our approaches. And indeed, we'd be showing robustness to a worst case spacecraft navigation and control failure. So if we're going to have several spacecraft that are performing these rendezvous in an autonomous fashion, we would also want them to be subjected to these safety requirements, and we would want them to be able to guarantee this. So it's indeed very important for full autonomy to be able to ensure that collisions can be avoided. So traditionally, passive safety is enforced through the design of trajectories offline and on the ground. This is done by understanding the orbital mechanics of the problem and going from there. Typically, there's several ways to do this, but you in fact just get a reference trajectory that you then track. Prior research in this area has then moved from going offline to an online implementation, where the idea would also be to deploy this on an autonomous kind of spacecraft. And in this case, the safety constraints are enforced by propagating the current state at a given time forward to several future times, and ensuring that none of those states enter your terminal set S sub f, as we've denoted it here. This has been implemented in a convexified approach and using the full non-convex constraints, but in essence, you create a very large optimization problem. Our approach is a bit different. We characterize the unsafe state space offline using reachable set theory. So this would kind of be visualized by this area here. It's a 6-dimensional region of state space. And then online, what we're going to try to do is ensure that the target does not enter the unsafe state space, such that in the event that all thrusters fail, you would passively drift away from these sets and you never enter. Whereas if you were inside here, you would passively drift in there. And by doing this, we've created a smaller optimization problem that is easier to implement on board. So we actually characterize the unsafe state space by using backwards reachable sets, and we can do this recursively by these two equations. If we have a terminal set S sub f, which represents our approach ellipsoid or our keypad sphere, and we can successively calculate the sets of states that would enter the terminal set in a given number of time steps at the final time. And it's fundamental that we do this without any control because that's what passive safety requires. Also, because the portion of the rendezvous that we're interested happens so close to the target, linearization of our dynamics relative to the target is actually very accurate, but it also has the added benefit that it preserves ellipsoidal sets in the BRS computations if you have an ellipsoidal terminal set. And we can see this right here. So this would be a backwards reachable set between a prior time and the final time, and indeed it's just a function of your state transition matrix. And because our target is in an elliptical orbit, which is periodic since it's unperturbed and Keplerian in this case by assumption, we're going to get time-varying backwards reachable sets. So what we're going to see is that even if wherever you put an approach ellipsoid, let's say you put it either here or here, and you take a step backwards or in time, or 2 or 3 steps, doesn't really matter, the ellipsoids that result from that mapping from a prior time to the final time are going to have a different rotation with respect to each other, and might also even be extended differently or amplified differently in some sense. This is a result of the time-varying nature of the dynamics here. So we would have very slow dynamics at apoapsis, so perhaps smaller changes on our ellipsoids here, and we'd have much faster dynamics at periapsis and perhaps much larger changes in our ellipsoids over here. So recall our definition of the backwards reset over an interval, where we found basically the set of states that would enter the terminal set in exactly n steps or less at this final time. So if we were to start here, and we've already defined a horizon n, or a number of steps n, then we would have found a set of states along the orbital arc, or relative to the target, that would slowly but surely be propagated naturally and end up going inside of the terminal set at this exact moment in time. We're interested in staying outside of this. So again, the backwards resets are unsafe sets, and we're trying to stay outside of those. By being outside of those, in this case, if we just use this expression, we would guarantee that we would not collide at this moment in time. However, we could collide before or even after, so we have to take that into account in our analysis. So if we want to be safe with respect to multiple target positions or along the orbit, we can parameterize that by the final time. That's why I'm saying we can be safe with respect to many final times. We need to take a union of the backwards reset over an interval. So at every moment in time, we have a different backwards reset over an interval because of our LTV system dynamics, and therefore if we take the union across the orbit or for a sub-portion of the orbit, we can at least maintain safety for a certain period of time. In our case, because we don't know the exact duration of our maneuver, we're going to do this for the entire orbit, because that way we can maintain n-step safety across the entire orbit, and we have just a general safety result. As a conservative measure, we're going to stay outside of this entire union of backwards reachable sets. We decided to use model predictive control in this work because the goal was to develop something that could potentially be used on board. So we need to have quick solutions. And if we have a linear safety constraint, which we will be talking about in the next slide, then this formulation just ends up becoming a quadratic program. And so once we solve that optimal control problem, we can just compute that we take the initial control and apply it on our full nonlinear relative equations of motion. So our control model is LTV, but our full simulation is done using the nonlinear equations of motion. And the QP is particularly important because if you're going to do this on board, you need to have something that is able to be solved quickly, and that's important for systems like satellites that have very limited computational resources. So since we've already characterized the unsafe state space, which I'm kind of showing by these weird ellipsoids on the right, we actually have a non-convex constraint. That is, every state in our horizon should be outside of this union or this volume of state space. We use an approach here that locally convexifies this safety constraint. So basically we Imagine we had some states in our horizon. We actually project this radially onto that surface, and we figure out where's the point that is furthest away from the origin, because this would locally approximate the exterior of this union. And then we use the tangent at that point to set up a half-space constraint on every step in our horizon. We do this for every point in our horizon, and then we implement that in our model predictive control scheme. So now that I've talked a little bit about the theory, I'll talk a little bit about how we implemented this in code in our algorithm. We've split the problem into really 3 phases, but the most important ones are these 2, where we first maintain passive safety with respect to the approach ellipsoid, and then we maintain passive safety with respect to the keep-out sphere. So again, if we have an initial condition, we do all of our radial projections, we construct our safety constraints, and then we solve our QP, apply the control, update our state, and we repeat this until we enter a region that is near the approach ellipsoid by this, and it's labeled by this bounding box, basically. Once we enter this region, we trigger the phase change. And now, because the approach ellipsoid backwards reachable sets are a superset of these guys, by definition and construction, we are automatically going to be passively safe with respect to this guy, as long as this was done appropriately and correctly, which we will show that it has been done. Then we repeat the same process, and again, once we get close to the keep-out sphere and we enter a bounding box around it, we trigger another phase change and we get rid of the safety constraints and we go to our final approach. This might mimic, for instance, or simulate the final docking procedure. And that's exactly what we see here. We see in the blue trajectory the implemented solution by the MPC. And if I were to sample particular points along this trajectory and propagate them forward without any control, they would drift away from the approach ellipsoid, as you can see here. Same happens once we enter the keep-out sphere phase. You see the actual passively safe approach trajectory, so we're getting closer, but in a way that if a failure occurred at any of these given moments, again, we would just drift away and we would never enter the set and collide with our target body. We can confirm this by looking at whether our states along these blue trajectories are ever members of the union of backwards reachable sets. And indeed, they're never inside until we've triggered the phase changes in the mission approach. So we can show that we never enter to the discretization level those sets, and therefore we are passively safe. So here I just kind of want to show an animation of how this works. We're approaching the approach ellipsoid in a safe way. We've sampled these trajectories. They drift away over time. Now the keep-out sphere phase begins, and the same process happens. As we get near it, if failures were to occur, they never enter the keep-out sphere. And then finally, we go in for the final approach. So here I just want to compare the safe versus unsafe approach. The maroon trajectory in this animation is the unsafe one. And if a failure occurs at the exact same time, highlighted by this red dot, if you take that state and propagate it forward passively, we see that in this top case, it passively enters the set, and in the bottom one, it does not. We can see more examples of samplings that are unsafe right here. So we have several states that, when sampled and propagated forward, would enter that terminal set. And here we show the case if we had a 3D approach. So we have some out-of-plane component in this delta z direction. We can see that the approach is indeed passively safe. None of these sample trajectories enter the approach ellipsoid. You can see the out-of-plane component there being corrected, and therefore this other drift occurs in the in-plane motion alone. And again, we can see from here that in the set membership that we are indeed passively safe. We don't enter the sets that we've computed until we've actually triggered the phase changes in our mission. This could be motivated by, let's say, insertion errors in your launch or whatever, and you're not precisely at the same initial condition that you hoped for. And indeed, yeah, this is a very generalizable process, and it works for myriad initial conditions. So in conclusion, we've developed a fail-safe control policy for Rendezvous on generic elliptic orbits using backwards read sets. So we've been able to demonstrate and show that in the event of total thruster failures, we prevent the chaser from colliding with the rendezvous target or the approach ellipsoid or the keep-out sphere. And therefore we are passively safe and will not have collisions in the event of that worst case failure mode. And future work will look into extending this to active safety, and we will be demonstrating and showing the existence of abort maneuvers once we've entered the keep-out sphere phase for that final approach. So thank you very much for listening and for having your attention. If you have any questions, feel free to contact me. My email is here below. And yeah, I'll be happy to answer any questions as well live in this session.